67 is a really, really good problem. This is section 3.1. This is one of those problems that if I don't get any questions about it, I know nobody's doing it, because it's weird. And if you don't understand why there should be a problem in homework like that, you don't understand homework. Of course there's going to be problems in there you don't immediately know how to do. That's the purpose of homework. So this one says find a second degree. So find a second degree polynomial where, and then they give you some stuff. Where'd it go? There it is. P of 2 is 5. P prime of 2 is 3. And P double prime of 2 is 2. So then you stare at the problem and you say, problem, create more words, problem. The shit are you talking about? Now, I'm not looking funny. You read this thing and you feel like there's not enough information, but there's a lot of information right here. Right? What does the second degree polynomial look like? Ax squared. All right then. So you see how they give you a lot of information. Plug a 2 in, you're supposed to equal 5, right? Okay, what does that look like? Do you see? So that's the step people skip. You don't write this for yourself. You got to give yourself something to work with. It's just like a normal word problem, except now I'm writing a whole function to work with. Instead of Bob and Fred made $5,000 last week. Bob made 100 more than twice Fred. So you have to give them something so I can work with it. Here I have to give myself the function. It's there. That's a general second degree polynomial. Bam. So I could do one of two things. I could either, what's P of 2? Well, that's going to be 4A plus 2B plus C, and that's supposed to equal 5. Well, that's good information. How many unknowns are in there? How many unknowns? How many unknowns? How many variables? Count the letters. 3. So how much information do I need? How many equations do I need total? 3. I have 1 so far. I have 2 more things they told me. Hey. What's P prime of X?
2ax plus b.
And then P prime of 2 is supposed to put a 2 in. It's supposed to equal 3. Yeah, keep going. Use all the information. I love it. The key step that's really easy to miss is writing this for yourself. That's the answer. I just wrote the answer. There's the answer. I just got to figure out what A, B, and C are, but there's the answer. And that's what a lot of math is. Write the answer and then work with it so then you can figure out the unknown parts. So that's the answer, and just got a couple unknown things, or 3. You figure them out. Is that cool? You're going to end up with a system of equations. The beautiful thing is, what's P double prime? 2a. And so when you plug a 2 in, it doesn't give a shit, there's no x left. It's supposed to equal 2. You know what a is. So it's not even a real system of equations, right? You don't have to make a matrix or anything. Because I'm going to know a, then back here I'm going to be able to figure out what b is, and then up here I'm going to figure out what c is. All right, I've done the whole process. You just got to fill in the details. That's the key step, which is really easy to miss. I totally understand that, but you have to give yourself something to work with. Bless you. Anything else from homework stuff? Yes?
This is from 3.3.
Yeah.
A semicircle, it's like at the end of the exercises, a semicircle with diameter PQ sits on an isosceles triangle PQR to form a region shaped like a 2-dimensional ice cream cone.
Yeah. Okay, it's in here too. Yeah.
Et cetera, et cetera. It's the same, I think, in the book.
Yeah. Find the limit as theta goes to 0 from above of A theta over B theta. I love it. So they give you, all right, so they gave you an image, right? They gave you some dimensions.
Mm-hmm.
All right, so
Well, only the 2
So,
side dimensions.
exactly. So here's the idea. There's a semicircle sitting on, so we got an ice cream cone, basically. This is area of theta for both. Blah, 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 blah. blah, 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 blah. Where'd it go? Where'd it go? Oh, here. 10 centimeters, 10 centimeters. Here's theta. This is 10. This is 10. So what do I need to know to figure out the area of this triangle? So I can write an expression for this. They kind of give it away. The area is going to depend on what the angle is. So in order to figure out the area of this triangle,
Is it A equals pi over, or 1/2 BH base times height?
yeah,
Use
sure,
the-
of course.
that
In which
formula?
case, what do you need? Sure. So you can do 1/2 base times height. In which case, I have to know the, which kind of makes sense too. Because think ahead. What do I need to know the area of the semicircle?
Pi r squared.
Yeah. So pi r squared. I'm going to have to know the radius, which is half of the base of the triangle. So if I find what the base is of the triangle, I got two places I can use that. Right? This is all the questions asking what's the limit. I think it's as theta goes from 0 to 0, a theta over b theta. So it's all about, can you write expressions for these so you got something to work with. So that's how you kind of work through a problem. Okay, that's the question. I need to be able to write expressions for those. This is what they gave me. Oh shit, let me focus. What do I need for the area triangle? Okay, how do I get that from what they told me? Does anybody see how to get the height? And you know theta, believe it or not. You know theta. So they didn't tell me what the number is, but I know theta, and I know that's 10. So of course, how do I figure out what this is?
How do you know theta?
So,
Oh, is it because, okay.
because they haven't told me the value of it, but I need an expression with theta in it. So it's kind of like I'm going to use it. I'm going to say, I know this, it's theta. There you go. That's theta.
Okay.
Can you, all right, I'm not going to do much of this. Trig, right? Some trig going on. Also for the height, right? Right? But once you get the radius, you can use some good old Greek dude help you out, right? Really, his followers did all the work, Pythagoras. Poor followers did all the work, and he took all the credit. So you've got to get an expression for this. How do I do that? I use some trig. And I need the height too. And then I can get the area. And then I know what b theta is. I know what the area of the triangle is in terms of theta. I also kind of, in the process of this, I cut this sucker in half, the base, and I use that to figure out a of theta.
Can you assume that the base is the same as the sides?
Of course not.
Because of the shape. I mean, it looks like it's the same.
All they tell me is it's isosceles. In order for these to be all the same, it has to be equilateral. Theta has to be 60. Mm-hmm. But they said theta, so what could theta be? 20, 70, right? So it doesn't have to be. No, you can't assume that, because then the problem is too easy for this book. Yeah. I like it. So the whole thing is built on, I'm allowed to change this. Right? I want more ice cream. Let me open the sucker up. Right?
So you do like an opposite over hypotenuse or something like that?
Yeah. So like in this triangle here, this will be half the base, right? I'm going to call this x. But what's in this triangle? What's this?
Yeah.
Now some of you guys might realize there are other things you could use here. Side, angle, side. I don't know. That might bring up bad memories from geometry, but hopefully decent memories from pre-calculus. I don't know. There are other ways to do this, but you can break this into a right triangle, so then you can use trig. But what's this angle here in this triangle? What's this? What's this angle? Yeah. So somewhere in this, you're going to have to use some trig identities. Okay. And we know we can use with side, angle, side. Side, angle, side. Which law you could use? What's the law that kind of builds on Pythagorean theorem? Does anybody remember that? What's the more general Pythagorean? Pythagorean theorem only works with right triangles. Well, there is a more general one that works with any triangle. You guys don't remember. Okay. And you're all like, we don't remember, dude. What the shit? All right. So it's c squared equals a squared plus b squared minus 2ab cosine c, the angle that relates to this guy. So see, I know A, I know B, I know the angle that relates to C. No, yes? If theta was 90, what's cosine 90 degrees? Cosine of 90? No, I know 90 is pi over 2. What's cosine of 90 degrees? 0. Cosine likes x, 90, I'm all y. Cosine's going to be one of them C terms. Just pull his head in, 0, doesn't like it. All right, so that becomes the Pythagorean theorem at 90 degrees. Let that be frickin' cool as shit. This is an adjustment if it's not a right triangle. That's pretty cool. I don't care if you like math or not. That's just cool, that idea. That's an adjustment. Oh shit, it's not a right triangle. Let's do some adjusting. Oh shit. Okay, all right, that's enough. So really, this is all about write an expression for the area of the semicircle. What do you need for that? I need the radius. Oh, I need that for this too. That's beautiful. So one thing I'm going to do is going to be used twice. Kick ass. Right? And then you can investigate what happens when you divide them and take the limit. Okay. All right, that's enough of that. Now, obviously, I love that problem. There's so much stuff in there. I love it. Some of it very basic, and some of it really kind of dredging up the memories. If you do it this way, it avoids having to use some half-angle formula, right? I'll figure out what this whole base is, because it's using this whole triangle. I'm not using the right triangle then. I'm using the whole cone. Okay, enough. Anything else from homework stuff? Please tell me. That looks familiar, right? Does that feel familiar? Remember what was called the SSA, which I always call the ASS because of how it is. It's an S. It has two options. Do you remember that? It had two possible answers. You had to figure out both possible triangles. Does that sound at all familiar? Okay, all right. Scheisse. A few of you guys. Okay, anything else? Homework? No? Okay, so let's do this. Let's do a couple of chain rule review problems, and then I want to get into implicit differentiation, which sounds so yummy. I thought you'd use that adjective. Can somebody, I'm thinking about it. Did I leave that light turned off back there? Some way? Can you, Connor, can you, is one of those switches down? They're all up? Okay, it's just me. Okay. Chain rule. So, I'm really trying to get you used to this dy dx notation. It's the same thing as prime. This notation means the same thing. In fact, here's a little neat notation. Whenever you see a triple lined equal sign, that means by definition it's equal to that. These mean the same thing. Cool? So how do I do this? What's the inside function? Cosine. And a really good extra step maybe for some of us is to say, is that a constant? No, it's dependent on x. Cool? Therefore, I've got work to do. Otherwise, I just put a 0 if there was no x in it. Or no this in it, whatever the variable of interest is. There is one, shit, I got to do stuff. So cosine x is the inside function, and the outside function obviously must be e to the something. How do you do the derivative of e to the something? What's the derivative of e to the something? E to the something. That's the most beautiful derivative. times what?
Cosine x.
Yeah, the derivative of cosine x. Let me write it. Let me keep this thing going. There we go. Tighten that up a little bit. So that's all chain rule does. It's kind of a nice visual. You link the derivatives of all the inside functions as you hit them. So of course then you get, what's the derivative of cosine? Negative sine? E to the cosine x. You normally put something out in front of e to that so it doesn't get sucked in and sort of becomes a functional coefficient. Okay, that's the basic idea of chain rule. Yes?
So what if you replace like e with like a y? Would you bring for the first portion?
All right, so there's a few things that, what is this?
Or another x? Just something that cosine, if cosine or sine or trig function was in the exponent.
Ooh, all right, are you talking about if I did this?
Yes.
Ooh, okay, can't do that yet.
Okay.
I really want you to see. This is in the form constant to a functional power. I know how to do those. If I had a functional thing to a constant power, I know how to do those. So what's kind of wrong with this? Which rule do I use? It's both. We will do these. They are so neat, and I know you expect me to say that, but I love the idea that the process we're going to use is very straightforward, but then at the end you end up seeing how both parts of the answer are each related to doing each of these ideas. It's neat as all shit, but we're not there yet. We don't know how to handle that yet. I like it. There's too much going on there. In fact, think about the function x to the x. Just that guy. If you really start to think about it, it really trips you out. If I put a negative 1/2 in there, can I do it? And this is assuming I want to be real, which is it's always true unless I say otherwise. Can I do negative 1/2? Because it would be the square root of negative. I can't do that, right? But what about negative 1/3? I could do that all day. I could do a cube root of a negative number. You guys with me? So it seems to be define, not define, define, not define, define, not define. It's freaky as all shit. Your calculator gives up anyway. Try to graph in your calculator. It's not true. You'll see something over here, but you won't see shit over there, and that's not really true. But it's like, I can't handle that shit. Like, we understand calculator. That's where the humans come in and say, oh, I can't do it. Poor little calculator. We're better than that. Anyway, sorry. So that's late. We're not there yet. It's obviously one of my favorite little functions. Okay, let's do one more of these chain rule bits, and then we'll get into some implicit. Let's see, what about if I had tangent of cosecant of square root of 7 minus x. Okay, so this is where people get all freaked out. You are eventually going to have to worry about all this shit in there, but the first step is what's the derivative of, well, what's the outside function? What's the outside function? Tangent. Tangent's got a bunch of shit in it, right? So the first step is just, what's the derivative of a tangent of something? What is the derivative of a tangent of something? Secant squared of that thing. Times the derivative of what goes in here. What goes in here? Yeah, cosecant of, let me go ahead and rewrite this thing. We know we're eventually going to have to rewrite this. And do you see how I really want you to see this? So now it's like you've given yourself a new problem. That's your new problem. This other shit just comes for the ride. It's done. Come for the ride. Come for the ride. I could have given you this problem instead. One less level. Did you guys see that? I took care of a level, now I got the other levels inside. So now I treat that like its own problem. This is why you don't have to know ahead of time how many links you're going to have. How many times you're going to do chain rule. You don't have to know that in the first place. You just do it as you hit it. Do I have to use chain rule again? Of course, I got shit on the inside. I like it. So, secant squared, cosecant, 7 minus x, times, what's the derivative of cosecant of something?
Negative cosecant times.
I got a cosecant of that thing. I think you said it. Cotangent of that thing. Times, so that's the derivative of cosecant is here. You guys see how this is not a product. Does everybody see that? This is not cosecant times, no, it doesn't make any damn sense because CSC by itself don't mean nothing. Okay. Canadian Skater Corporation. Oh. But it doesn't mean nothing to Matt. Times what? What goes here? Yeah, the derivative of 7 minus x to the 1/2. Kick ass. Yes, sir.
Where'd that 1/2 exponent come from?
Oh, it's been there from the beginning. It's the square root.
Oh,
So
okay.
yeah. Sorry. You automatically rewrite roots as you're doing it or before you do a derivative. Here I could do the first without worrying about it, but then I'm like, I'm going to eventually have to worry about it. All right, so we get, now you start to understand what I mean when I say you need a little math stamina to get through some of this shit. Times, let me go and bring that negative out here. Is that cool? Bop. Just take any constants out front as you get them. Times cosecant of 7 minus x to the 1/2. Cotangent of 7 minus x to the 1/2. Times, how to do this guy's derivative? Is it a chain rule? Is there an outside function? Yes. What's the outside function? 1/2 power. What's the inside function? 7 minus x. Beautiful. How do I do something to the 1/2? Derivative. Anything to the 1/2. How do you think it's derivative? 1/2 comes down. Times the thing. To the times the derivative of 7 minus x, which you can just write, what is it? -1. Woo! So let me bring out my constants. So there's a -1/2 that can come out here that kills this negative, so it's 1/2. I got no other constants here. I don't want to rewrite all this shit. You'd have 1/2, blah, blah, and blah, blah, times dividend. And you can bring that down if you want to. It doesn't really change anything if you do. You guys see that? I didn't have to know ahead of time it was going to be this long. Every time I did it, done. New problem. Done. New problem. Right? Do you guys see that? Yes, no. Just, you got a lot of writing to do. Aw. Just keep track of what's there. Okay, so you guys are realizing, yes, doing some of these problems takes more than one page. This wouldn't really, you might want to do this one. Okay. All right, so let's get into, let me lead us into this next section, because it comes right off of this. This is section 3.5, I believe. It's cool, I like it. Yes?
For these questions, like on the exam, are you gonna want us to try and distribute all that out and reduce, like, or, because it's still multiplication?
True, but is there really anything you can do? Can you make this cosecant squared? Trick question, because that's inside the secant thing, right? So is there really anything you do? The last thing I could really do is just bring this down if I want to. There's really nothing else I could do.
So that would be the acceptable answer?
Yes. But unfortunately, I will take points off if there is something you can do and you don't do it. And I don't mean like to make it look prettier or something obscure that you would never see. I mean, if you see cosine squared x plus sine squared x and you don't make it 1, you're losing points. If you see a 1/2 here and a 4 there and you don't just make it frickin' 2, you're going to lose a point, right? It's a little spacing simplification. I like it. Okay, so let me ask you this. Let me do a really simple chain rule thing, and this is leading into the next section. Oh, get out of there. Let me just say I have, what's the derivative of, what you got, Jeff? I don't know. Actually, let me see. There's two things I want to do. Let me do this other one first. Sorry. When I do y equals, doesn't matter, x squared. Using the other notation, not the prime notation, how would I do the next step to take a derivative? What would I write here? Do you see how you took the derivative of that side? This kind of makes sense. What do you do in algebra? What if you do something on one side? You better do the other side. So I'm taking the derivative of both sides, right? And on this side, what do I get? 2x, I like. And just, all right, that's, stop right there, right? So when I take the derivative of y, why isn't that just 1? Because y is dependent on x. Right? But what if I did, do you guys remember I said chain rule is always there? What would the chain rule say here? What's inside? X. So then I have to do dx dx, right? But what is dx divided by dx? That's 1. That's why it doesn't show up. When the inside function is just x, I don't really have to do chain rule because it would just multiply by 1. But the reality is we always do chain rule. Okay. This all has a purpose. All right, that's one thing I wanted to really highlight is this comes out because I'm taking the derivative of y. So wherever y was, the derivative of it would be dy dx. I like it. So that's one thing. Here's something else. Let me see. So what if I had this here? What would this guy's derivative be?
8. So that's 5 to 7 times derivative of 7x.
Right? No, and then you make it 7. Ooh. That's not my point. So what if instead, and you got more work to do. I don't care. It's not my point right now. What if instead I had f of x equals sine x? I know I wouldn't write it like this, but just, oh well. Do you see how it's still fundamentally the same external idea? Stay with me now. There's a purpose to this. So what would df dx be? Same first step, right? It would be 8 times sine x to the 7 times d by dx of the inside. Now stay with me. This is the heart of this section. People mess up in this section because they don't realize. It doesn't matter we're shit. The function, something to the 8th power. How would I do it? So let me capture the idea. Let's capture the idea. If I had any function of x to the 8th power, what is the idea of how to do it? So y is some function of x. Which one? Any. Maybe sine, maybe 7x plus 5, maybe whatever the hell else I want. How do I do this? Whatever this function is, what's the first step always? Yeah, the 8 comes down. 8 times y to the 7th times derivative of y. Doesn't that capture exactly what we did there? What was y in this problem? 7x plus 5. So I took its derivative. What was y in this problem? Sine x. So I took its derivative. Stay with me now. So, here we go. Let me see if I can... I've never quite shown it this way, but I do this eventually, but I like doing this first. What if I had then this equation? And I don't want to solve for y. That's just gross. I want to take its derivative. I want to take this equation's derivative. Nothing's really different from before. What's the derivative of x squared? 2x. What's different here, though? What is y? What am I, in fact, let me be really specific. Let me write here. Find dy dx. And this is why this notation is actually better than the prime notation. The reason we use prime notation in the beginning is just so we don't get too confused. We just focus on the rules we're learning. Now I want to bring this back in. Why is it so important? Because I know exactly what I'm taking the derivative with respect to. Prime hides that. Very soon we're going to be taking derivatives with respect to some letter that affects all the letters inside of there. That's going to be related rates. Oh shit. But right here I'm doing dy dx. So what's the derivative with respect to x of x squared? 2x. Right? Is that cool? Now what happens here though? Y is how related to x? Y is how related to x? It's some... We can do this. Y is a function. A function of x. I just don't know what it is. Couldn't I solve this for y? Couldn't you solve this for y? Yeah, and then I know what the hell y is. Explicitly as a function of x. This is an implicit definition. Hence the name of this differentiation, implicit differentiation. Don't see what y equals directly. Just work with it implicitly. It's like, ooh, I don't want to tell. So what's your something cubed? What happens to something cubed? What happens? The 3 comes down. Y to the? But then the inside gets a turn. What's the derivative of the inside? Dy dx. Kick ass. Kick ass. And again, just to remind you, what's really here was dx dx. That's 1. That's why it didn't show up. But here, that's dy dx. Oh, shit. It's going to show up. Do you know what that is? No, this is what I'm trying to figure out. Equals. Yes, because you got to do that to both sides. Now it's algebra. What's it asking me for? Dy dx. Take a minute and solve for dy dx. Get dy dx by itself. Figure out what it is so we can answer this question. Right? Is that still going? Hopefully it's got space. This is algebra. So if I add that, subtract that, that's always a good first step. These just switch places. And then I can divide by this. Where did my square go? Divide that by that 3y square. Now an interesting implication of this is that in order to figure out the slope of this curve, what do I put into here? We normally just put an x value in, but here I have to actually put in the whole point. So let's do one that we can actually reason it out geometrically. Right, this is kind of a gross thing to think about. What does it look like? Let's do one that sort of looks like that form, and it's a lot better. Anybody tell me what the equation represents here? Yeah, it's a circle. Kick ass. What's the domain? Yeah, it's got radius 4. So it goes from -4 to 4 because the center is 0, 0. Hasn't been translated at all. And of course, the range is. You officially cannot solve this for y. I know you think you can, but you can't. What do you end up getting? If you try to solve for y, you get 2 answers, so you can't solve for y. And in a little bit, we'll see equations that you can't even solve for y to plus or minus. You cannot get y by itself. They're very easy to create. You just jumble the x and y together. There's no way. This one I could have solved for y. All right. So if I attack this, so here's the circle. It's negative 4, 4, 4, negative 4. My circles always look like, yeah, there you go. Basically, it's like Stewie's head. It's a deflated football from Super Bowl a while back. Tom didn't know anything. So take this guy's derivative to figure out what dy dx is. So let me just start going. 2x plus 2y times dy dx, exactly like we did here. So whenever you take the derivative that has a y in it, it's going to have that chain rule piece. That's all this is chain rule. Equals 0. I like it. So dy dx equals, subtract 2x, divide by 2y, the 2's cancel. Now let's try some, this is something I can see. I can see what's going on here. What should the slope be if I plug in the point 0.04? What should I get? I should get 0. It's flat there, right? And sure enough, if I plug in 0.4, I get 0. What should be the slope here? At 4, 0. Undefined. And 4 over 0 right there. Right? And what should be the slope? What's true about the slope for any point in here? What's true about this slope? It is it positive or negative? Negative. I like it. So all the slopes in this quadrant should be negative. And what's true about the x and y in this quadrant? They're both the same sign. They're both negative. So x over y would be positive. It's now negative. Yes? No? So if I knew a point, if I knew what this point was, I could plug the parts of the point in to see what the slope is there. That's kind of new. We used to only have to put an x in. Now it's got both x and y. I got to put both in there. Kicking the ass in. Just to take this a step further that you don't want to take it. What do you get if you try to solve this for y? So subtract x squared, right? So 16 minus x squared. Take a square root so I get my plus or minus. So please take a minute and take that guy's derivative. So rewrite this, obviously. And I can apply the rules. Hopeful. Is that cool? And then if I rewrite this a bit, the least I would want you to do is to bring this out front and kill the 2's. Let me also bring this sucker down. And I'm kind of ignoring the plus or minus. Let me bring the plus or minus back in here. Kind of just put that aside. I really want you guys to see this. This is kind of cool. What is this? What is this? What is that? What does that equal? What is that?
Y.
Why? Did we get the same answers before? Yeah, we got the same answer. So, nothing amazing. There's no David Blaine moment, but this is just not solving for y, and I can get dy dx. If I'm able to solve for y, I should get the same answer. And we did. Yes, no? So it's just an organization, and math didn't give a shit what we do first or second. So here I did not solve for y. Here I did solve for y, but then I put back in, I unsolved for y. I put that back in. You guys kind of see what I'm saying? Okay, maybe. Okay. I understand this is some freaky shit, but it's really just chain rule for when I've got y in a piece. It is a function of x. It has to get its own chain rule piece. Let's try another one. And then I'll give you a couple to try on your own. I'll get out of there, g of x. Oh, that crap. Sorry. Okay, this looks yummy. So again, the instructions would say dy dx, find dy dx.
Let's see that. You doing right? Yeah. Okay.
This is where those of you who have done what I said to do, you're kind of used to it, write the rule, then do the derivatives on the next step. With this shit, it becomes really huge. How do I do this guy? What is it fundamentally? Yeah, but what rule is it fundamentally? Chain rule. I love it. That's all I got to know right now. I don't even have to worry about what's in there. Just shit in there, inside the e, chain rule. How do I do that then? Derivative of e to the xy? What's the first step? What's the derivative of e to anything? E to that thing. Oh, I love you, e. Times the derivative of the inside. I'm going to worry about that later because I got other shit to worry about right now. It's the people that try to do too much at once. Because you want to get done so fast. And I'm like, well, you got the wrong answer really quick. What about this guy? It's sine of something. What's its derivative? Cosine of that thing. That thing is y, which is a function of x. So what do I have to tack on? The inside function has to get a turn. Is that cool? You guys see that? It's sine of something. What's the derivative? Cosine of that thing times the derivative of that thing. What people end up getting from this lecture is they just start throwing dy dx onto everything. Holy shit. Does this first piece have a dy dx on it yet? No, I haven't done the derivative of something with y in it yet. Right? It's only when I actually have the derivative of something with y in it. What about this side? What is this side fundamentally? What rule? Product rule. It's the derivative of x squared. Okay, I think you know that one. It's all right. That's 2xy plus. Is there a dy dx on this? Why not? What did I take the derivative of? X squared. The inside function's x. You don't need shit, right? This next one, though, x squared, what's the derivative of y? Dy dx. Kick ass. So it's only when you are taking the derivative of something with y in it or y itself. That's when dy dx has to show up. It's really, this is the culmination of everything we learned so far. It's just like, okay, there's something inside. I don't know what it is. I've got to do chain rule for that shit. Now I got one last derivative to do. And this is a lot like that was. This is just a product rule. Cool. Derivative of x is 1, so I get y plus x. Derivative of y is dy dx. Now here is where people really start to freak out. I don't know why. Now it's algebra, right? I remember my teacher going, the rest is algebra. People are like, show us the algebra. Well, I mean, what do I have to do? What is it I'm trying to find? dy dx. So now I got to solve for dy dx. How the shit do I do that? If you wanted to, you could put like an m here or something. Right? Because what is dy dx? It's an unknown thing. Let me call it m, because sometimes it helps you keep track of, I'm trying to get m by itself then, if you want to. What do I have to do first to start to solve for dy dx? So if I had this problem, yeah, there, sure. What would you do first to solve for x?
Distribute.
Okay, it's the same problem. Same shit, same problem, right? Same problem. So what do I do first? Distribute, so I'm able to get my like term shit together. How do you solve an equation for x? Get all your x stuff on one side, everything else on the other side. How do I solve for dy dx? Get all your dy dx stuff on one side, everything else on the other side. It's the same. It's the same. The basic rules cannot change. So you have y e to the xy plus x dy dx e to the xy minus cosine y dy dx equals. Here's that math stamina coming in. 2xy plus x squared dy dx. So I need everything with a dy dx in it on one side, and everything else. Just get all the x's on one side, all the numbers on the other side. It's beautiful. Doesn't change. No dy dx. You're going to move over. No, yeah, this has the dy dx. So I basically just have to switch these. This has no dy dx. Oops. So I'm going to subtract this guy, because it's got a dy dx in it, and I'm going to subtract this guy over here because it don't. And then what's the last couple steps?
Factor dy dx.
Yeah, take the dy dx out and then divide by the shit you don't want. Let's see if you guys can handle. So if I take a dy dx out, I'm going to divide by all the other stuff. I'm going to divide by x e to the xy. Is that cool? I'll take a dy dx out, and then all the shit that's left, I'm going to divide by it. X e to the xy minus cosine y. Got it. Minus x squared. Kabam. Ermagerd. Yes, and if you are looking at this like, well, there's a lot of parts there, I don't get over that shit. This wasn't really difficult. Now, there are two components to this. There's a piece that you got to get over, the chain rule idea. So people have to understand why dy dx shows up and why it doesn't show up sometimes. That's one hurdle to get over. But then solving for dy dx is algebra. That's all it is. Could you solve this original equation for y? If you can, teach me, right? Show me the way. Okay? How in the world could you solve this for y? If you want to drive yourself insane, try it. But trust me, I have made it so that you cannot solve that for y. If you try to graph this sucker, it's going to look something, woo-hoo! These functions we're going to deal with look so freaking cool. Because they're not functions, number one. Is this really a function? No, because I can't solve for y. It's not really a function. You get these funky ass shapes from this section. In fact, they should have, please tell me. Yeah, they have beautiful pictures. Oh my God. You get the butt graph, of course. What's the butt graph? That's this guy, the cardioid, right? A little sideways heart. No, yes, cardioid. No, yes, maybe, a little bit. But then you get some really freaky shit. You get the Campbell of Eudix. And where's the witches one? Oh, well, there's all these nifty ass. Anyway, so there's some cool stuff to look at. So let me give you a problem to try. Let's see. What you got, Chuck? Wait, let me make it. Yeah, yummy. What you got, Chuck? I don't know, man. There, that's I'll make one side, not two you.
It's X e to the Y, right? Not just one.
Yeah, x e to the y. I gotta remember, a while back I decided to try to make my y's more extreme. That's almost too extreme now, but oh. X e to the y. Alright, that's pretty good. I don't know what to do. I should just put the word y. So it's gonna be like, what's the width and the height? Oh,